Hiya. Okay, so finally, we're going to move away from the binomial distribution. Um, so what we've kind of seen in class, and we haven't gone too much over this in the last 2 weeks, but one of the things we saw was that, like in the very first week, that there was different distributions, right? There's the Bernoulli distribution, there's the discrete uniform distribution, there's the continuous distribution. We've now seen, maybe I should write this down. So we got Bernoulli. We got some guy named discrete uniform. We got some guy named continuous uniform. And then we had the binomial. And then we also saw that there's a normal distribution. So there was the normal one. There was the Poisson. Like we saw 1.5 million distributions. And so now we're going to say, okay, like, can we take a more nuanced approach, right? So when we looked at this binomial distribution, we saw we were able to calculate what its expected value is, its standard deviation. We were able to get a lot of information, right? We were able to approximate it. We were able to do all these things. Now what we want to ask is, well, can we do this with all of this? Is there a way to kind of do this? And the way we're going to do this is something that we've been missing in this math class so far. If you think about it, we've had, and the big thing we're missing is variables. Like we've had some variables, right? Like obviously in the last section I had n, we had r, we had x, but we never said let x equal, or like find the value of x, or So you know what? We're going to go back in time, back in our algebra days, and we're going to start looking for x and trying to solve these problems. So we're going to be adding variables, aka random variables, into our probabilities. And this is actually going to let us take our distributions to the next level, in essence. So basically, like a lot of the times we've been writing p of 3 or something, and stuff like that for the probability of getting a 3. But in this case, this can be represented as subset 3, etc. So let's see. We're going to try to generalize this. So variables themselves are actually, in mathematics, they're used as placeholders. And actually, the first time variables were used was in a math textbook by, I think it was Descartes. I'm forgetting exactly who right now. No, it was someone else. Oh, I'm forgetting who. Anyway, it was used as basically, what they said is we let x, y, z be arbitrary variables that we don't know the values of. So letters in the end of the alphabet. And then we let a, b, c be variables that we do know the value of. And so this is why x, y, z became very popular. So everyone started using this book. I'm forgetting the name of the book. But yeah, so it started becoming super popular. And now we use x, y, z for everything. If you ever want to know why x and y, it was basically some book one time and the whole world took off. Anyway, for us, we're going to, since we've been using a lot of lowercase letters for a lot of our like smaller things like n is equal to, or mu is equal to, or r is equal to, etc. We're going to let capital variable letters be our variables. So like we'll do like x and y, for example, as our variables. And they can be anything you prefer, right? So like, for example, in essence, the idea is like if I'm rolling a die, instead of saying the number 6 is rolled, I'm going to replace the 6 by a random variable. So I'm going to say the number x is rolled, right? I don't know what x is, and I don't really care in essence, right? Think about a Bernoulli a uniform distribution. They all have the same probability. So it doesn't matter if I'm calculating for 6 or 1, I'm going to get the same distribution. And so here we only care about the number x. And so when we're looking at these variables in this way, this x is called a random variable. And so this is different than variables in other ways. So a lot of the variables we've been talking about is just kind of normal variables. The book calls them dummy variables, but no one really uses that term. They're just normal variables. But these are slightly different. These are really used only for events. So when you're looking at an event, this x is going to be replacing this event. So let's look at an example. Like this x doesn't have to be equal to some number. So it can be like the number x is rolled on a die. Here, let me highlight these in green. The number x is rolled on a die. That's one way we can use the random variable. We can say the side x of a coin is flipped. Notice how I'm saying the side x. So it could be the side heads or the side tails. I don't know what x is, but it could be either of the two. And we don't mind either way. Or the number x is drawn out of a hat. Notice how we don't say what is actually pulled out. We're just saying let this be some variable. We don't really care what it is. And so how does this work for like plugging things in? So if I were to have the number x is rolled, and I say x is equal to 6, well, what does this mean? What this basically means is my sentence, the event, becomes the number 6 is rolled. So I just replace x with 6. If I were to say x is equal to 3, so if I make x equals to 3, what this basically means is the number 3 is rolled. And notice how all I'm doing is I'm replacing the variable x. Well, what happens with our probability then? Well, what we can do is we can place it into our probability function and just say probability of x equal to 3. What's the probability that x is equal to 3? And this is literally the same question. It's asking what is the probability of probability that the number 3 is rolled. So when we put in a value, that's when we can actually ask the probability. So normally we had been doing something like this, but now this is being converted into this. Now you might be asking, well, okay, Aram, like, why can't we just use P of 3? This is going to get so complicated. Why are we using x's? Like, leave x's to find their own problem, like relationship problems. We don't got to deal with this. But the cool thing is that we can actually use this notation to get a lot more information. So like, for example, like at this point, like why not, like, yeah, so I think I just said this verbally, why not just keep P of 3 like before? But this actually allows us to expand our things a lot more. So like, for example, if I want to know the number rolled is less than or equal to 3, well, now I can just write this as P that x is less than or equal to 3. What did we have to do before? Beforehand, we had to say, well, what's P of 0 plus P of, or I guess there's no 0 on the dice, so P of 1 plus P of 2 plus P of 3. That's, for me, a lot more difficult than P is less than or equal to 3, or x is less than or equal to 3. This is much more concise. Now imagine if I had a 3,000-sided die, and I say, what's the probability it's less than or equal to 1,000? You're not going to sit here and write this 1,000 times. Ain't nobody got time. It's much more easy to write x is less than or equal to 1,000. And so that's why we're going to be using this new notation. It helps us generalize in a nice way that allows us to much more firmly and better write our everything, kind of. So, okay, well then how about, let's look at something a little more complicated. How about if we can't do something like this? If I can't do x is less than 3, how do I look at just regular subsets? So like, for example, if I have, let A be the subset 2, 4, 6 of all even numbers and find P of A, right? So this, in other words, how do we write this in our new notation? In this case, it is a little more nasty, but what we do is we say, okay, what is the probability that x is contained in A, where A is equal to 2, 4, 6. If you think about this, it's actually not that nasty, right? Because this, either way, we're going to have to write this down. Either way, this part, we have to write down. There's nothing a way around it. What this is doing is making this be shorter, right? So this, if we wrote it the other way, I would have had to write P of 2, for 6. And so it's a tiny bit different, but it's basically the same idea. And as we kind of said, a random number doesn't always have to represent a number, right? It can represent a variable. So I'm trying to see how long this is, because this lecture is getting long. Yeah, we should be okay. This might be just a longer video. If we look at a coin, so if we're looking at a coin flip, we could have that x is equal to heads, right? So x, and then we just represent as x is equal to h. We say, when is x equal to h? So yeah, I think you're starting to, like, at this point be like, okay, I think I'm starting to understand where this is coming from. I promise it's going to be super weird in the beginning. What I'm going to do is let me stop here for this video. We'll do a little pause. And then in the next video, I'll kind of continue this explanation, and hopefully hearing it a second time will help solidify a lot of the things we're doing, and see how this probability gives us a distribution and stuff like that. So I will see you in the next video.